Hello all, welcome back to the next session of DRS. Okay, still we are in the beam session. Sorry, not deep beam. We are at the next phase of doubly reinforced section. How to do an analysis of DRS beam. So, what is the doubly reinforced section? I hope everything you know from the previous section. Analysis. I hope already I told you somebody is going to give you a beam. Okay, so they were gonna show you some beam. You see this beam, how much moment the beam can take, like that they can ask you a question. So you know visually you can see width, depth, cover they have provided and what are the number of reinforcements are there. So they will ask you a single question, how much moment the beam can take. See, obviously the answer will be, if it is 300 beam and 4 bars of 3 bars of 20 mm, 3 bars of 16 mm, approximately 150, 120, 200, only in that range the moment will be there. Answers will be in that range. But anyhow, how to determine that? Okay, so in this session we are going to see that analysis and then we will solve some 4-5 problems in the topic in this session. Okay, so if you have paper pen, please take paper and pen and sit, pause the video, draw the figures, write the equations, and also there will be problems are coming in this session. Please take calculator with your hand. You can pause the video, solve the problem and verify. But anyhow, I cannot do that. I cannot waste the space, size, everything. So I will continue the session. Okay. So they will give you, to analyze a beam, they will give you the width, depth, cover, AST, how much reinforcement the bottom. So remember that they cannot, if you in analysis problem, you can only see bottom 5 rods. It won't be AST1 or AST2, right? Practically nobody knows which bars is for AST1, which bars is for AST2, because all the bars are at the same location. Please remember, analysis, try to use always compression side, because there is no formula which to determine which is for AST1 and AST2. Always we will use AST and ASC as a single thing for analysis. For design you should do separately. For analysis, always single formula, AST and ASC. Okay. So step 1, obviously similar procedure what you followed in a singly reinforced section. Step 1 is to determine XU max. What is the maximum distance the neutral axis can go. Step 2, find XU value. The little different here is, how do you determine the XU values previous section? C equal to T. Total compression force equal to total tensile force. Here also C equal to T. Here the compression is depends on two things. Not only concrete. Concrete only they cannot take compression like singly reinforced. Here the compression is also taken by some steel bars. Correct. So the C1 is, we already know, it is 0.36 FCK B into XU from the singly reinforced. C2 is the extra compression taken by the steel bars provided at the top. You can see that ASC. So force is nothing but stress into area, so FSC into ASC. What is T value? See, I told you T can also be written as T1 plus T2, but here I am writing T only because of there is no difference between AST1 and AST2 when somebody is giving you the bars. They will tell you 4 bars, they will tell you 6 bars. Nobody gonna tell you 2 bars of 20 mm dia for AST1 and 3 bars of nothing, 0. So T is same formula, force into stress into area, 0.87 FI into AST. So equating everything, you will get the XU value. That is the step 2. Okay. Same procedure, equating compression equal to tension, you will get the neutral axis. Step 1 is determining the XU max. So if you go step 3, if you already the same procedure, if XU is lesser than XU max, it is under reinforced section, even in doubly reinforcement case. Even for doubly reinforcement, you can reach the over reinforced section, right? You can put more and more bars and reach the over reinforcement. So the step 3 you are checking like XU is lesser than XU max or not. If it is under reinforcement, it's cool. Use this formula. There are two formulas for compression force and tension force. Compression force, again, bending moment, you know it is force, bending moment is nothing but force into distance. Here there are two compression force are acting, C1 and C2. You can go to the previous figures and check, there are two compression force here, C1 and C2. So C1 will act L1 distance, C2 will act L2 distance from the T. Correct. So what is C1? Exactly the same formula used for a singly reinforced section, 0.36 FCK B into XU. What is L1? L1 is the lever arm distance from the C1 to T value. I hope without figure I am explaining, because this is the same thing we are discussing for last 3-4 hours of sessions. Okay. So L1 is D minus 0.42 into XU. The new thing which is coming up is C2 and L2. What is C2? C2 is the compression force because of the extra steel, that is FSC. Stress into area is FSC into ASC. Where it is acting? It is acting at a distance of D minus D dash. Okay. It is acting at the distance of, you can see this figure, ASC, that is acting at a distance of D minus D dash from that AST. Okay. So this is the formula for calculating the MU value based on compression force. based on tensile force. If they have given you 2 bars for AST1, 3 bars for AST2, then you can use this formula. That's what I have explained clearly at the bottom. They will never give you. So it's always you try to use the compression force formula. Okay. Anyhow, so what is the theoretical formula is force bending moment is force into distance. There are two steels here. Some steel is for taking mu limit, some steel is for taking mu minus mu limit. Okay. So T1 L1 plus T2 L2. T1 is nothing but stress into area 0.87 Fi into AST1 into L1 is D minus 0.42 into XU. What is T2 is the force because of the extra bending moment, that is 0.87 Fi is the stress into area is AST2 into the what is the distance this is acting, this lever arm distance is D minus D dash. I hope it is very clear. It is very simple. You pause it, any doubt you can ask me. It's very simple. Everything is clearly explained here. So now suppose if XU is equal to XU max or if XU is greater than XU max, you know balanced section over section, the same formulas here based on compression and tensile force use instead of XU max, that's it. Instead of XU use XU max to determine the if it is balanced or under over reinforced sections. Okay, clear? It's very simple. Analysis is step 1 find XU max, step 2 find XU and determine whether it is under or over reinforced. Under reinforced use these formulas directly. If it is over reinforced use these formulas with XU instead of XU, it is XU max. I have told you what is XU, what is XU max, all those stories previous sessions. I hope you know clear. Okay. So far we have I think I made you clear how to do an analysis, how to do and design in doubly reinforced section. Okay, I am moving to problems. So one typical simple example problem. So what is the maximum strain in the compression steel? Because we never discussed the strain at that particular location, right? It's totally different. We know because it is coming inside the concrete. Okay, for steel we already discussed 0.002 plus 0.87 Fi by ES in the singly reinforced section at the bottom. What is the strain experienced by the compression steel? That is a question they are asking. So it's there. I am using a similar triangle procedure. Okay, it is not ESC, it is epsilon SC. So epsilon SC, I am using similar triangle. Okay, 0.0035 is for the maximum strain taken by the concrete. So opposite by adjacent, 0.0035 by XU is equal to epsilon SC divided by XU minus D dash. You keep epsilon SC one side, bring everything other side. This formula will give you the strain in concrete, the strain experienced by the steel in the compression zone. Clear? It's very simple, only similar triangle. If you know this figure, obviously you will move in a minute to the next problem. Okay. Next question. So they are asking a concrete beam, 350 mm width and 700 mm depth. It is subjected to superimposed bending moment of 300 kN meter at service conditions. Okay. So they have given a moment. They are using M15, Fe4 and 5. They have given FSC. So it's very easy, or else you should use 0.87 Fi. And they are asking amount of tensile and compressive steel. So it's a design problem. So they are asking AST and ASC. And they have given effective cover of 50 centimeter. 50 centimeter. Give me a second. Sorry, this effective cover is 50 mm. Okay. So this is a clear design problem. They have given width, depth, FSC, Fy, FCK, everything and also cover. So I am going to design AST and ASC. So given I have told you B, they have given 350, effective depth 700, D dash cover at the top is 50 mm, FCK 15, Fy 4 and 5, FSC 350. Okay, and they are given service moment is 300. So I am multiplying the load factor. Always if they are service moment, you have to multiply by the load factor 450 kN meter. Okay, so I am starting the step 1. What is step 1? MU limit. This is a design problem, right? You can go back. You can step 1 is MU limit 0.138 FCK BD square. This is because of Fi is 4 and 5. FCK is given 15, 0.138 into 15 into 350 into 700 square. Okay, everything is given. Just substitute. You will get answer of 355 kN meter. This is the maximum moment the beam can take if it is a singly reinforced section. And what is the given service moment? It is 450. Correct. So 450 is more than 355. So you cannot design it as a singly reinforced section. You can go for doubly reinforced section. Now step 2 is calculating the AST1. Okay. So AST1 is, so to determine the AST1, that is the step 2. So you know 0.8, you know MU limit already calculated. You know Fy, you know D value, you know XU max value. I think you should know XU max value because Fy is 4 and 5, and then you can determine the AST1. You can see this one. AST1 I have determined as, substitute everything, you will get 1750 mm square. Okay. So next, so this is the reinforcement required for this mu limit. Mu limit is nothing but 355. Okay, so for 355 kilonewton meter, you need 1800, approximately 1800 mm square. What is the extra bending moment is available there? Extra, because the customer asks for question asked for 450. Okay, 450 kilonewton meter, and you have designed for 355, approximately 95 kilonewton meter is pending. For that extra 95 kilonewton meter, you should put AST2 and ASC. That's what the next step is. So you know the formula, 0.87 Fi AST2 into D minus D dash, everything is given, find the AST2. So club both AST1 and AST2, approximately 2164 mm square. That's it, area of steel is over. For the same extra moment of that 95, you should design the compression steel also, that is on the right side. So moment is equal to force into distance. Force is nothing but stress into area. FSC into ASC into D minus D dash. FSC is given, D is given, D dash is given. Keep ASC one side, bring everything other side. Compression steel is 413 mm square. I will give you one hint, very critical hint. Okay, remember approximately AST and ASC will be always 1 by 5, 1 by 4 times. Okay, the answer is 2000. The answer is 400. It is approximately 1 by 5. Clear? Nowhere ASC will be 2000 meter square. Nobody will put. Okay, remember that your answer will be only 400, 500, 300 for this compression steel ASC values. Okay, so next one, next question. So you can pause and solve yourself. Anyhow, I will explain. A simply supported beam of 8 meter span, RCC beam, 300 mm, 500 mm depth. They are asking, they are given 4 bars of 25 mm bars at effective cover of 37 point from the tension phase, and they are 4 bars of 25 mm bars. Okay, and FCK is 25 and FY is 4 and 5 bars they are given, and they are putting 2 bars of 60 mm diameter in compression side with an effective cover of 50 mm, and they have given the FSC value. They are asking how much moment it will take. It's a pure analysis problem. Okay, you note down everything, all the given. You see, B is given, D is given, D dash is given, Fy is given, small d effective depth is given, FSC is given, FC is given, FCK it is, FCK is given, AST is given because 4 bars of 25 mm bars, ASC is given, 2 bars of 60 mm dia, everything is given clearly. So analysis problem, I hope I told you clearly. Step 1 is determine the XU max. It's 0.48 into D value is 462, you will get 222 mm. Step 2 is determine the XU value. XU value is direct formula, 0.36 FCK is C1 plus C2 equal to T, that formula. 0.36 FCK B into XU plus FSC into A is equal to 0.87 FI AST. You substitute all the values, have the XU value 209 mm. So neutral axis is lesser than XU max, so it is under reinforced section. Step 3, then use the formula directly, 0.36 FCK B into XU minus C1 L1 plus C2 L2 formula. Directly you have everything, just substitute everything, you will have the bending moment it can take is approximately 270 kilonewton meter. Okay, so very simple. So direct formula substitution. So I will give you for the same question they are asking. Next question is, okay, so anyhow you can pass it here, you can solve yourself. Okay, and then you can verify the answer. It's very self-explanatory, all the slides are. So next question is, for the same question above, what is the extra live load the beam can carry if the factor of load factor is 1.5? That's what they are asking. What is the extra superimposed live load the beam can, not is extra, how much live load the beam can take? It's very quite simple. So they are given 1.5 as a load factor. How to answer this? They have taken a density also 25, everything is given. So we know the beam ultimate moment the beam can take is 270. That's what from the previous answer we know. Divided by 1.5 because of the factor they have given. So the moment you should design is for 180. Okay, the maximum moment the beam can take for the given condition is 270, and you use the load factor 1.5. So approximately you should design for 180. We know the bending moment you should design is for 180. What are the overall load they asked you to consider? Dead load and live load. So total load is dead load plus live load. What is dead load? It's a self weight of the beam. So how to know the self weight of the beam? It is, you know, density equal to mass by volume, weight by volume. You weight equal to density into volume. What is density of the concrete? They have given 25. What is the volume? You know the length of the beam. You know if per meter you can calculate because everything is per meter. Okay, so per meter means only the area. Okay, understood, right? For you can see the dead load I calculated for per meter because The live load also you can answer it in per meter. So you know per meter means length into breadth into depth is volume. Length you don't know. So I am putting as a 1 meter. So you will get answer as a per meter. So length into width is 0.3 and 0.5. You multiply everything density, you will know the dead load is 3.75 kilonewton per meter is the dead load of the beam, weight of the beam. Okay, and we know bending moment is WL square by 8. Okay, since L is per meter, you will put L equal to 1. Okay, so W square by 8. So W is nothing but dead load plus live load. Dead load, you know, you substitute everything, cancel it, you will get the value of live load as if you see the bending moment is 180, you substitute all those values, you will get the live load 18.82. So you can have a superimposed live load of maximum 18.82 kilonewton per meter you can have. Okay, so it's a very quite big number if you say. Okay, so clear. If somebody is given you beam, from there you can back come calculate the moment it can take. From there you can calculate how much live load in the building you can have, means like how many students can study, how many chair and table can you can put, something like live loads you can calculate coming back from the beam. Not like you somebody 100 people has to sit and designing the beam. It is like coming back. If the beam dimension is this much, how much load, how much people can live there, like a live load. Okay, people's everything. Like a classroom or like a hospital or something like that. Okay, this problem is very practical if you say. So I think this will be the last question for the doubly reinforced section. One more time, a doubly reinforced concrete beam has a width 300, effective depth of 500 mm. The beam is reinforced with 2200 mm square of steel in tension side and 628 mm square of steel in compression side. The effective cover at the top is 50 mm. They have given. Assume both the tension and compression style yield, means like they are asking you to take the FSC value both for the same. The FCK is M20 and FE 250. Okay, so the stress block parameters for concrete and steel, they are asking to find the stress block parameters, nothing but depth of neutral axis they are asking, first one, and then they are asking moment of resistance, how much moment the beam will take. It's a pure analysis problem. Okay, so coming first, but also they are asking for neutral axis anyhow. So given is B, D, AST, ASC, D dash, FCK, FSC, everything is given. Okay, so it's very easy, right? You know all the formula to determine the neutral axis. C1 plus C2 equal to T. You put all those values, you will get the neutral axis is 158.3 mm, and then the moment of resistance is direct formula substitution 0.36 FCK, again C1 L1 plus C2 L2, substitute everything, you will have the bending moment it can take. Again you see 200 kilonewton meter. Okay, please remember all those answers. You see this problem, what is the beam size? 300 cross 500 beam with 2200 mm square and 600. I told you, I will give you two hint. You see the AST value given is 2200, ASC value 628. It is approximately 1 by 4, right? Approximately 1 by 4, correct? So always remember when you are designing or when you are seeing some answer, AST provided at the bottom and ASC, it will be always approximately 1 by 4 will be the area. Okay, and the bending moment values, you see this question answer, all the beam size, they will never give you a beam size 1 meter, 4 meter and all. The always the beam size also will be 300, 500, 250, 400, 300, 600, something like that. So for this ratio, always the answers are around 200, 250. You see this question answer is 200. Last question answer is approximately 270. You see the answers will be also in this range. So when you are solving any exam, RRB, any type of exam, when you are solving, when you are getting some answer around 400, 500, it's stupid, it's wrong. So you have done a terrible mistake. So please remember, more than formulas, you try to memorize the answers also. So what can be the range of your answer? What can be the range of steel? You cannot have a AST values 4000 mm square for a residential building. Obviously, you see the beam dimension, you can never have 4000, 5000 mm square. And for ASC, you cannot provide 1500 mm square. It's stupid. Okay, so you should also know the answers like formulas. Okay, I have tried to give you some inputs and I will try to give you some inputs throughout the classes also for the next what can be the slab dimensions average, what can be the footings dimensions and everything in the future classes. For now the beam moment I have told you 100 to 200 average for singly reinforced section, 200 to 250 to 300 average for doubly reinforced section. This can be your answers. And AST approximately, if it is doubly reinforced section, 2000 to 3000 to 5500 mm square. Okay, ASC will be 1 by 4 to 1 by 5. Sometimes it can go to 1 by 3 depending if the depth is high. Because depth will take some bending moment, so the ASC value will come down. Okay, so have these answers in mind and sum these 2-3 formulas in your formula sheets have some formula sheets also. So far we have 5-6 formulas over, and the end of this RCC you will have some 15 formulas. Okay, so thank you until we see you in the next session. Okay, thank you.